Hello, so this lecture would be for the Combinatorics class based on bonus textbook section 8.2.2 on products of exponential generating functions. So this would be very similar to the products of ordinary generating functions. First, we have a lemma. So if I have if I have two sequences and I have their exponential generating functions, so a and b, and I define another formal power series in this way, where the coefficient of x to the n over n factorial can be written in this way. The lemma says that a times b is equal to c. And the proof is basically, so it's similar to before. So when we take the product of these two power series, we will get general terms of this form. And if I multiply them, so I have a sub j times b sub k, and I have x to the j plus k divided by j factorial, k factorial. And now in order to get to what we want, which is something with a binomial coefficient, I will multiply this by 1 and write the 1 as j plus k factorial over j plus k factorial. And I basically switch the position of these two. So now I have this term times this other term, j plus k factorial over j factorial k factorial, which is exactly the same as the binomial coefficient, j plus k choose j. And this product would be of degree n if and only if j plus k is equal to n. And so the coefficient for x to the n over n factorial in the product a times b is the sum of all the ways that you can get a sub j times b sub k and j plus k choose j. And so there are all of these terms. And so we get exactly what we want to prove the lemma. And now we can use the lemma to prove the product formula for the exponential generating function. So just like in the ordinary generating function, I have a sequence a sub n where it's the number of ways to build a certain structure on an n element set. And I have another sequence b sub n, which is the number of ways to build another structure, possibly the same structure, on an n element set. And then I have a third sequence, c sub n, which is the number of ways to separate the set 1 through n into the disjoint subsets s and t, where s and t are disjoint, and their union is exactly 1 through n. And then after I do this separation, I then build a structure of the first kind on S and a structure of the second kind on T. And let capital A, B, C be the exponential generating functions for the three sequences. And the product formula says that all you have to do is multiply A and B to get C. All right, so the difference between this product formula and the product formula for the ordinary generating function is now you're told that you can separate the subset 1 through n into two subsets, not just two intervals like before. So that's the differences between this current product formula and the previous product formula from using ordinary generating function. All right. And so to prove that, we can use the lemma. So if we separate the set 1 through n into S, N, and T, let's say the set S has I elements, then there are n choose I ways to choose the elements of S. And then there are A sub I ways to build a structure of the first kind on S. And then you multiply that by, so now once you choose S, the rest of the elements that you haven't chosen would be T. So now all you have to do is multiply with B sub n minus I to compute the ways to build a structure of the second kind on T. And this will be true for all I between 0 and n. And so to get C sub n, you just need to take the sum of all of those. And so comparing this with the lemma, we get what we need. All right, so let's apply this formula to a problem. So here I have a football coach who has n players to work with at today's practice, and the coach splits the players into 2 groups, and then the coach asks the members of each group to form a line. So both groups would form a line, and then so for the first group, we would ask each member to choose to either take an orange or white or blue shirt. So there are 3 options. For group 1. And then the second group doesn't have to do anything. So here it says that the member of the second group keep their red shirt, but that's not really relevant to the problem. And the question is, in how many different ways can all of this happen? And right now we're going to use the exponential generating function to solve this. All right, so let's say the coach selects K people to form the first group. So let A sub K be the number of ways to, so let A sub K be the number of ways that these K people can take an orange or white or blue shirt and then form a line. So first, let's see. So to take an orange, white, or blue shirt, that would be 3 times 3 times 3 K times. So that would be this number. And then the number of ways to form a line for K people is K factorial. And that is why we have A sub K is equal to K factorial times 3 to the K. And so by definition, the exponential generating function for this sequence is just, so by definition, that's starting from 0, we have A sub K, and then we have x to the K over K factorial. And so because A sub K is this, we can write that, and then I can cancel out the K factorial, and that would give me all right, so yeah, so I've accidentally written these twice. So let me erase that. But so now after I cancel k factorial, I get exactly this power series. And so using the geometric series, I get 1 over 1 minus this ratio, which is 3x. Okay, so we've computed the exponential generating function for the first group. So now assume there are m people in the second group and let b sub n be the number of ways the m people can form a line. So that's just m factorial. And so the exponential generating function would just be, by definition, the sum of b sub n x to the m over m factorial, starting at 0. So then I would just replace b sub n with m factorial. And again, I can cancel the m factorial, and I get 1 over 1 minus x, again using the geometric series. Okay, so now let c sub n be what we actually want. Let c sub n be the number of ways the players can follow the instruction of the coach. And let capital C be the exponential generating function of the sequence c sub n. So the product formula tells us all we have to do is multiply a and b. And we've already computed a and b, so I get this product. And right now it's, so that's good. So this is the exponential generating function for c sub n. And now I want to use this exponential generating function to find a closed formula for c sub n. So right now it's not in the form that I know like how to rewrite this as just one power series, but this looks like something that you can simplify, or like you can write this as a product of two power series using, if you first do the partial fraction decomposition. Right, so here is my work for the partial fraction decomposition. So at this step, I just plug in 1 and 1/3 in order to get 0 here and here. And so I get my A and B, and actually these are maybe not very good choices because I've used A and B, so maybe let me do like, well, let me do like alpha and beta. Okay, so then that tells me that I can rewrite capital C as the sum of two things that look like geometric series. Right, so then this is C. So I get this because of the 3x, and I get x to the n because of this is just 1x. And next I will just move the extra 3 inside, and that's why this is n plus 1. And I also move 1 over 2 inside of both power series here. And now I can combine the 1/2 3 to the n plus 1 and minus 1/2 to give me this, and then I have x to the n. Okay, so now we're almost done. So normally when we were working with the ordinary generating function that we were working on before, we would be done. But C is not an ordinary generating function. C is an exponential generating function. So we have to do one more step. So to find a closed formula for C sub n, we do this following computation. So from earlier, we have that. And now I just want something that looks like x to the n over n factorial. So I just multiply n factorial over n factorial. And so this box is exactly the coefficient for x to the n over n factorial in C.